An oligonucleotide, derived from the meaning of oligo, few nucleotides, is a chain molecule composed of common building blocks known as phosphoramidites or activated nucleoside monomers, either DNA or RNA. An oligonucleotide is set in a specific sequence, opposite but similar to its binding target, known as reverse complementary. There are different types of oligonucleotides, which include natural RNA molecules such as miRNA, siRNA, or primers, and also include synthetic oligonucleotide molecules such as antisense oligonucleotides, which are often abbreviated ASO, or sequence-composed non-natural bases such as linked nucleic acids, or LNA. Oligonucleotides are generally made by chemical synthesis, a process based on solid-phase phosphoramidite synthesis, SPS, but may also be synthesized by liquid-phase oligonucleotide synthesis, LPOS methods. These molecules are typically modified with protection groups, which enhance both chemical synthesis and clinical function. SPS and even LPOS methods generally share common steps executed in a cycle. The process begins by linking the first phosphoramidite of the sequence to a solid support group or resin using a long-chain linker. The cycle of synthesis then begins with the removal of a DMT protection group in the first step, known as detrotylation. A second chemical activation step of the next nucleoside phosphoramidite monomer is triggered by the addition of a catalyst. The base functional group of this phosphoramidite monomer should also correspond to the next appropriate monomer, which will continue the target sequence. The newly activated phosphoramidite monomer, or base, is then rapidly reacted in a third step. This reaction couples the new phosphoramidite monomer to the 5' end hydroxyl group of the previous base, extending from the growing sequence, which is immobilized on a solid support or bound to a core structure used for liquid phase synthesis, such as homostar support. At the end of each coupling, any unreacted hydroxyl groups at the end of the molecule are then capped via acetylation to prevent deletion mutations, degradation, or formation of unwanted side products. The fourth step oxidizes the newly formed phosphotriester linkage between the two nucleotides. The cycle is repeated to elongate the growing oligonucleotide until the oligonucleotide has reached the target length. Finally, the oligonucleotide is then cleaved from its solid support in a process of ammonolysis or ester hydrolysis, and additional protection groups are removed using caustic reagent. Solid-phase phosphoramidite oligonucleotide synthesis is so prevalent because it achieves rapid and relatively inexpensive custom-made oligonucleotides of a specified length. Much like other pharmaceutically relevant small molecules, oligonucleotide synthesis requires careful control with respect to temperature, pH, quality of substrates, etc. Because of the typical methods used in oligonucleotide synthesis, the longer and more complicated the nucleotide sequence, the more difficult it is to meet yield, purity, and cost objectives. To learn more about the optimization of oligonucleotides using PAT technology, visit mt.com/oligo-synthesis.